In chapter 3.1, we talked about the different measures of central tendency, or the different types of averages. So 3.1 was calculating your averages, which we talked about the mode, the median, and the mean. Now in chapter 3.2, we're going to talk about the different measures of variation. And variation, the root word for that is vary. So let's take a look at the first one. The first one is the range, and that is the difference between the largest, so difference meaning to subtract, between the largest and smallest values of the data distribution. The range is greatly affected by extreme data values, and we talked about those being outliers. So the median was not affected by outliers, but the mean was, and so is the range. So let's take a quick example that we're going to look at in 3.2. A large bakery regularly orders cartons of Maine blueberries. The average weight is supposed to be 22 ounces. Okay, the average weight, so average is mean, median, and mode, and in this case it's talking about the mean. So the average weight is supposed to be 22 ounces. Random samples were weighed from each supplier. So you have supplier 1, so this means one box of blueberries was 17 ounces all the way up to 27 ounces. And supplier 2 is a different, although 17 all the way up to 27. So it says first calculate the range. So we're going to calculate the range for supplier 1, and the range is the largest number minus the smallest number. So you have a range of 10 ounces. Supplier 2 would also be 27 minus 17, 10 ounces. So if you were comparing supplier 1 to supplier 2 and you only looked at the range, then you'd say, well, there's no difference between these two suppliers. All right, now it said that the average is supposed to be 22 ounces. Well, let's see if it actually is. So for supplier 1, we're going to calculate the sample statistic mean, or X bar. So you would add up 17, 22, 22, 22, and 27. You add all of those up and you get 110. And there are 5 numbers, so for both of these, n equals 5. And so I'm going to divide by 5, which gives me 22 ounces. So that's what it was supposed to be. So supplier 1 is holding true to their word. All right, supplier 2, the sample statistic X bar, add 17, 19, 20, 27, and 27. Well, you get 110 again. There's 5 of them, so that also gives us 22 ounces. So far, the mean, they're the same. The range, they are the same. So both suppliers appear to be exactly the same. Well, then that leads us into the other 2 types of variations. So here was the first type of variation. Here is the second and the third types or measures of variation. It's what we call variance and standard deviation. Now, the variance and the standard deviation, they tell us the measure of the spread of the data, how spread out are your numbers in relationship to the mean. And in our example, the mean is 22 ounces. So in each set, are the numbers close to this mean of 22 ounces or spread out from this mean? Now, X minus X bar, this is the difference between what happened and what you expected to happen, because what we expect to happen is the 22 ounces. So the X here would be an example. If we were looking at X minus X bar, I expect to get boxes that weigh 22 ounces. Well, in reality, there was one time where they got a box that was 27 ounces, so they got an additional 5 ounces in that box. But there was also a time when the box came in, you expected 22 ounces, but you only got 17. So in that case, that box was down 5 ounces from what you expected. So this you would be okay with because you got more blueberries. Here you might be a little unhappy because you might be running a little short. So this represents a deviation away from what you expect and is a measure of risk. So now what we're going to do is calculate the variance and the standard deviation and look at those formulas. All right, so calculating the variance and standard deviation. Now, the book goes into 2 different formulas. One is called the defining formula, and one is the computation formula. What we use, because I feel it is the easier of the 2, is the computation formula. So that's the only one that I'm going to show you. That's the only one that you're required to use. If you look in the book, this formula appears or sometimes looks like the easier of the 2 just when you look at the formula, but in all actuality, this one is the easier to calculate. All right, so what we're going to first do is look at how to calculate the sample variance. Now, we've already talked about and have calculated the sample mean, and that symbol is X bar. The symbol for sample variance is S squared, so you need to be familiar with that. And here is that formula. Now, again, I promise, it looks a whole lot worse than it is. This is the summation of X squared minus the summation of X raised to the 2nd power divided by n minus 1. Then once you calculate the variance, it's just one additional step and you have the standard deviation, because the standard deviation is just S, so all you have to do is take its square root. So what we're going to do is calculate the variance and the standard deviation for that previous example that we did that dealt with the blueberries. All right, so we have supplier 1 and supplier 2. And we are going to implement this formula. Well, in order to get the values we need to apply this formula, I need to create a table that has the X values, and then we're going to square each of those values. Now, your X value is each data value. If you remember, it was a sample of 5. So it was 17, 22, 22, 22, 27, and supplier 2 also had a sample of 5, and it's 17, 19, 20, 27, 27. All right, so these are our X values. Now what we're going to do is square each of these. So what you'll want to do is go in your calculator and you're going to do 17 squared and push enter, and that gives you 289. So we're going to do that for each one of these. Now, this does not happen in this example, but I have seen it happen in other examples. Be careful if one of your X values is a negative number. Because if I go to my calculator and I put in negative 17 squared, it's going to give me negative 289. And this is why you have to be very, very careful with your calculators. If I want a negative number to be squared, remember, a negative times a negative is always positive. What my calculator is doing is squaring the 17 and then applying that negative. To correctly put it into my calculator, I would put negative 17 into parentheses, and then I would square it, and I would correctly get my 289. What you need to remember is that your X squared column will never, this column right here, should never, ever, ever have a negative value in it. All right, so now we're going to do 22 squared, which is 484. There's 3 of those. And then 27 squared is 729. Let's see, we already squared 17, that was 289. So now we need to square 19, which is 361. And we're going to square 20, which is 400. And then 27 was 729. All right, so once we get our tables, then what we have to do is we have to do their summations. And summations just mean add them up. So what we're going to do is find out the summations. So I would add up this column, which is 110, and then I would add this column, which is 2,470. And I'm going to do the same over here. And I get 110, 2,508. These summation values are the numbers that we're going to use in this formula here. Okay, now just so you can see the formula as I plug it in, I'm going to rewrite the variance formula right here. Uh-oh, my pen's going out. Let me switch pens. It's not going to be that nice, neat blue. Here we go. We have the summation of x squared minus the summation of x to the second power divided by n minus 1. Okay, I want you to be able to see that formula as we plug it in. So we're going to calculate the sample variance s squared for supplier 1. So the summation of x squared is this column, 2,470, minus here, this is the summation of x, 110 to the second power divided by n, which is 5, divided by 5 minus 1. Now, when putting this into your calculator, you need to be careful. One, it's the best practice to put all the numbers into the calculator and hit equals once. If you calculate this and round it and then round again, you've done so much rounding, your answer is going to be slightly off. So we can put it all into our calculator, hit equals once, and get the correct answer. Here is where the parentheses need to go. So let me show you how to put it into your calculator. You're going to do open parentheses, 2470 minus 110 squared divided by 5, close parentheses, divided by, open parentheses, 5 minus 1, close parentheses, enter or equals. So we get s squared equals 12.5. So s, which is your standard deviation, would be the square root of that. So the square root of 12.5, is 3.54 approximately. So I get sample variance of 12.5, standard deviation of 3.54. So now let's do that with our supplier 2. So s squared, my sample variance, is the summation of x squared, 2,508, minus the summation of x, 110 to the second power, divided by 5, divided by 5 minus 1. And again, my parentheses go when I start the numerator and when I end it, and then it's also enclosed in my denominator. So I would do open parentheses, 2508 minus 110 squared divided by 5, close parentheses, divided by, open, 5 minus 1, closed, equals 22. And then the standard deviation is the square root of 22, which is approximately 4.69. So you can see the variance, is different, as well as the standard deviation. So that is how to calculate the variations of the variance and the standard deviation. Now what I want to look at is symbol comparison between my population parameters and my sample statistics. You need to be able to distinguish between these. It is very, very important. So, population parameters and sample statistics. We have calculated the mean, and the population parameter symbol is mu. The sample statistic is x bar. We have also calculated the variance, which is sigma squared is your population parameter, s squared is your sample statistic. And we have also calculated the standard deviation, which is sigma for the population parameter and s for the sample statistic. Very, very, very important. So, what do the measures of variation tell us? So here's kind of a recap. The range tells us the difference between the largest or the highest value and the smallest or the lowest value. It tells us about the spread of the data, but does not tell us if most of the data is or is not closer to the mean. Your standard deviation is based on the difference between each data value and the mean of the data set. The standard deviation gives an average of the data spread about the mean. The larger the standard deviation, the more spread out the data values are from the mean. The smaller the standard deviation indicates the data tends to be closer to the mean. All right, another concept we need to look at is what is called coefficient of variation. What the coefficient of variation does is it expresses the standard deviation as a percentage of the mean. Now, here's when we use this. It's used to compare variability between two groups of data that have different units. When we were comparing supplier 1 to supplier 2, we were looking at ounces to ounces. But what if we have different units of measurement? That's what the coefficient of variation is meant to be used for. We abbreviate it CV, and the larger the CV, the more variability in the data, meaning more spread out around the mean. So here are the formulas that you need to know, and it's basically standard deviation divided by mean times 100. Now, we will always do it based on a sample, but if for some reason someone was calculating the coefficient of variation on a population, it is still standard deviation. It's just now we're talking about sigma divided by the mean, which is mu, times 100. So they're in essence the same formula. It's just if you look at the formula, this one uses population parameter symbols, this one uses sample statistic parameters. All right, so let's look at the example we have here. The mean, or the average yearly salary of all employees at Perfect Printing is $42,500, and the standard deviation is 4,000. The mean number of years of education for the employees is 16, and the standard deviation is 2.5 years. Calculate the coefficient of variation and compare. Well, here's why we have to use the coefficient of the coefficient of variation, because we are comparing salary to years of education. Well, how do you compare those two? Is $1 equivalent to 1 year of education? I sure hope not. So that's why we're going to convert them into percentages so we can compare a percent to a percent. All right, so here's the mean for the salary. Now, one other thing I want to point out, this does talk about all the employees. So because of that word all, I know that we are talking about the population. So in this case, it would be mu for the salary is 42,500, and the standard deviation is 4,000. And the years of education, we have the mean, or mu, is equal to 16, and the standard deviation is 2.5. So now what we're going to do is calculate the coefficient of variation on both of these. So coefficient of variation is standard deviation, so 4,000 divided by 42,500 times 100, and that is approximately 9.41%. Don't forget the percent sign, because we are converting this into a percentage. For years of education, it would be standard deviation 2.5 divided by mean of 16 times 100, and you get approximately 15.625%. Hopefully that's right. That's what I have written in my notes. So now we have converted these two into percentages, and I can then confidently say that the years of education has higher variability than the salary, which tells me that the salary, they are closer to the mean. If you found the salaries of all the employees, they're going to be closer to the 42.5 than years of education is to the 16. So that's what the coefficient of variation tells us. Then we move on, and the last concept that we look at in 3.2 is a theorem called Chevys Theorem. It is used to determine how spread out around the mean for any distribution. If you recall back, we talked about the different distribution shapes. We talked about symmetrical. We talked about, this is when, in chapter 2 when we did our histograms. We had bimodal, uniform, or rectangular, and we had skewed left or skewed right. So what this tells me is this theorem holds true for any distribution. What it states is, for any set of data and for any constant k greater than 1, the proportion or percentage of the data that must lie within k standard deviations on either side of the mean is at least 1 minus 1 over k squared. Okay, I'm going to show you how this works, but this is not something you have to have memorized. I'll show you here in a minute what it is that you have to be sure that you can do. All right, so the results of the theorem. So this is the important part. This is what you're going to be asked to apply in homework and on a test. It tells me that at least 75% of the data falls within 2 standard deviations. Okay, here's what that tells me. It tells me that Chevy Chev said, what if k is 2? So if I put 2 in place of the k, I get 1 minus 1 over 2 squared, which is 1 minus 1/4, and 1 minus 1/4 is 3/4. Well, 3/4 is 75%. So this theorem was used in order to give me the 75%. All you need to remember is that 75% fall within 2 standard deviations. And how that looks then in calculations is your mean plus or minus 2 standard deviations. So you're going to create an interval by taking the mean minus 2 times the standard deviation to x bar, or the mean plus 2 standard deviations. All right, what if we change k? So then what was found was at least 88.9% of the data falls within 3 standard deviations. So now k equals 3. So 1 minus 1 over 3 squared is 1 minus 1/9, which is 8/9. And if you would plug 8 divided by 9 into your calculator, you're going to get 88.9%. So again, what you need to remember is 75% falls within 2 standard deviations, 88.9%, or it might state approximately 89%, is within 3 standard deviations. So that would be x bar minus 3 times s to x bar plus 3 times s. And again, this is your mean and this is your standard deviation. And then lastly, the theorem said, okay, 93.8% of the data falls within 4 standard deviations. And where this 93.8% came from is by taking the theorem 1 minus 1 over 4 squared, which is 1 minus 1 over 16, or 15/16. And if you would go to your calculator and do 15 divided by 16, you're going to get 93.8%. Or it might sometimes state approximately 94%, but what you need to remember is then it is within 4 standard deviations, which would be x bar minus 4 times s and x bar plus 4 times s. So the part you need to remember, 75% gives me an interval within 2 standard deviations. 88.9% gives me an interval within 3 standard deviations. 93.8% gives me an interval within 4 standard deviations. So let's take that theorem and apply it to this particular problem. In 1881, Billy the Kid killed 2 deputies and escaped from a jail cell in the Lincoln County Courthouse in New Mexico. The distribution of artifacts, so what we're talking about here is artifacts, for 7 excavation sites sites found at this famous courthouse was. So we have 1, 2, 3, 4, 5, 6, 7. Each of these is an excavation site. 851 would mean in one of the sites they found 851 artifacts. In another of the sites they found 596 artifacts, and so forth. Now, given the sample mean, and that we know is known as x bar, so they added these up and divided by 7, and this is the calculation, and then it went ahead and found the sample statistic standard deviation for us as well. So this says to calculate or compute the coefficient of variation, and I need these 2 numbers in order to do that. So remember, the coefficient of variation is going to convert this into a percentage. So that is the standard deviation, 266.84, divided by the mean, 566.86, times 100. So when you calculate that, you get approximately 47.07%. So this is the variability. Now, one thing I want to state about the coefficient of variation, all the examples we have done have been calculated as a percentage between 1 and 100, because when we think of percent, we think of 100%. But please know that you could have a coefficient of variation that's 231%. It can be over 100, so don't think that it can't. All right, now we're going to apply Chevyshev's theorem. Use Chevyshev's theorem to find an interval, which means we're going to find 2 numbers centered about the mean in which at least 75% of the artifact counts for all of the such excavation sites would fall. All right, here's what you need to pull out of here. Chevyshev's theorem, 75%. That tells me that it falls within 2 standard deviations. So what we're going to calculate is x bar, 566.86, minus 2 times 266.84. So that's going to give me 1 number. And then in the interval, my second number will be 566.86 plus 2 times 266.84. And that calculates to 33.18 artifacts to 1100.54 artifacts. So this is the interval that falls within 2 standard deviations. This is called the lower or smaller interval value. This is the larger or the upper interval value. All right, next part to this. Use Chevys theorem to find an interval centered about the mean in which approximately 94%. Now, if you recall on the theorem, there was one that was 93.8%, and that would be approximately 94. So that tells me that we're looking for it to fall within 4 standard deviations. So I would do 566.86 minus 4 times 266.84 to 566.86 plus 4 times 266.84. And I do that calculation and I get negative 500.5 to 1,634.22 artifacts. But you might look at this and go, how in the world do you find negative artifacts? Well, you can't. So realistically, what this is saying is 0 to 1634.22 artifacts. Now, depending upon how the problem is worded on WebAssign, obviously we know this will be the upper interval value, but depending on how it's worded, if they want you to give the actual calculation or what really makes sense. So be sure that you read that very carefully on a WebAssign assignment. That completes 3.2.